Hi everyone! Today let's talk about section 11.5, lines and curves in space. So notation, the xy plane is often called R2, while the three-dimensional space is often called R3. A vector-valued function, gamma of t, is a function that inputs scalar and outputs vectors. Okay, so the output gamma of t can be thought of as the position vector of a moving particle at time t. As the parameter t varies, the function's gamma of t traces out a curve. We say that gamma of t is a parametrization of that curve. The path of the particle is a parametric curve. So if gamma of t outputs a two-dimensional vectors in the xy plane, we often write gamma is a function maps from R to R2. And gamma of t is of the form of, so we have two coordinates, x of t and y of t, so two coordinates here. So if gamma of t output a three-dimensional vector in the space, sorry, typo here, then we often write gamma is from R to R3. And gamma of t is of the form of, so it's a vector valued function, and we have three coordinates, so three components in this case. The domain of gamma is the largest set of values t on which all of the x of t, y of t, z of t are defined. So let's look at the following example. Parameterize each of the following curves in the xy plane. Okay, A, the portion of the curves y equals x squared between minus 1, 1 and 3, 9. So here, if we have y is a function of x or x is a function of y, we can use a natural parametrization. Okay, so what is that? So if y is a function of x, so in the xy plane, okay, then we can let x be t, then y is then f of t, right? If x is a function of y, then we let y be t, then x is g of t. So this is the natural parametrization. Okay, so for example here, we can let x be t, then y is t squared. So we usually let t be the independence variable. Okay, so then gamma of t in this case, we have x is t, y is t squared. And what is this? So we know y equals x squared is a parabola. Right, it's a parabola, and now we want to see between minus 1, 1, so this is minus 1, 1, 3, 9, so 3, 9 is somewhere there. Okay, this is 3, 9, so we actually want to draw this portion. Okay, so we're gonna restrict our t from minus 1 to 3 in this case. Okay, let me use a different color to draw that portion. So this is the piece. Okay, so you can also use other parametrization. Okay, so let me put this here. So you can use other parametrization, such as, well, you can use t cubed, then t cubed squared will be t to the 6. So this is also another parametrization. But however, if you use square root of t and then t, this is not good, because the square root of t is only greater or equal to 0. You only get from the 0 to the 3, 9. You cannot reach the piece from minus 1, 1 to the origin. Okay, so you have to make sure your t actually the curve it chase out really reach the pieces. Okay, so yeah, Be careful with that. Let's continue. Part B, the portion of the curve x equals 3 minus 2y squared between 1 minus 1 and negative 5, 2. Okay, so let's see here. We can let y be t because y is the independent variable. And then we have x is 3 minus 2t squared. So gamma of t equals x is 3 minus 2t squared, y is t. And then let's draw the picture. We know this is also a parabola, and because the leading coefficient is negative, so it opens to the left. Okay, if x is a function of y, then the parabola either opens to the right or to the left. But here, because the leading coefficient is negative, so it opens to the left, and it passes through the points 1 minus 1 and negative 5, 2. Okay, so and when the y is 0, it passes through 3, so we know it looks like this. Okay, so that's why my t is my y value, it goes from minus 1 to 2. Okay, so t is between minus 1 and 2. So far so good, everybody. Let's continue. Yeah, so here more generally, we can parameterize portion of the graphs of functions in R2 easily. Just like I said above, R of t is we let x be t, then y is f of t. Now we can have t goes between a and b. Then here, we can let y be t, and then x is g of t, when then t also goes from a to b. So far so good, everybody? Okay, let's continue. So next topic, parameterizing circles and ellipse. So example, find a parameterization for the unit circle in the xy plane. So unit circle, we have x squared plus y squared equals 1. And what does the unit circle look like? So it's a circle with radius 1 centered at the origin, right? And then we keep in mind the trig identities. One of the trig identities give us cosine squared plus sine squared equals 1. Okay, so we can also think about the polar coordinates. This is like t, and then this is the r is 1. Okay, so in this case, we will get so keep in mind the polar coordinates. If this is r, this is t, this is x, this is y, then x equals r cosine t, y equals r sine t. Okay, so in this case, because r is 1, so we just get x equals cosine t, y equals sine t. So gamma of t equals cosine t, sine of t, and because we want to have the whole unit circle, so t runs around. Okay, that's 0 to 2 pi. So far so good. Okay, what is the orientation of this parameterization? Well, when t is actually the angle made with the ray and the positive x-axis. Okay, counting counterclockwise. So that's why the orientation of this parameterization is going this direction. Okay, let me get back. What happened? Let's see. That's weird. Okay, I don't know why they deleted my. Okay, let's get back. Okay, so this is. Okay, so the orientation is counterclockwise. Part B, find a parametrization for the portion of the unit circle in the first quadrant. How about for the upper half of the unit circle? So in this case, our gamma expression still the same, but now our t for the first quadrant that corresponds to t goes from 0 to what is this guy? This is pi over 2, right? This is pi, this is 3 pi over 2, and then 2 pi will get back here. So that's why we have pi over 2 for the upper half, then the t goes between 0 and pi. Okay, so the restricted domain for t is gonna give us different portion of the unit circle. Okay, let's continue. Find a parametrization for the circle center at 1, 2 with radius 5. Okay, so what is the circle formula? We have x minus the x coordinates of the center plus y minus the y coordinates of the center square equals r squared. So far so good, everybody? Okay, so that's why now here we can see because r is 5, so we will have x minus 1 is 5 cosine t, y minus 2 is 5 sine t. Okay, and then we can also solve for x. X is 5 cosine t plus 1. Y is then 2 plus 5 sine t. Okay, so this is a circle center at 1, 2 with radius 5. All right. Okay, so why do I have this guy? Why do I set up 5 sine t, find cosine t? So if you have x squared plus y squared equals r squared, you set it up as x equals r cosine t, y equals r sine t. But here, instead of x, you have x minus 1. Then you just replace x by x minus 1 in the formula. And then we will have that. Okay, so gamma of t equals, so x is 5 cosine t plus 1, y is 2 plus 5 sine t. We also want to have the whole circle, so then t goes from 0 to 2 pi. All right. Part D. Let a and b be constants. Find a parametrization for the ellipse with equation. Okay, so in this case, you can see x over a squared plus y over b squared equals 1. So that's why the radius is 1. Then we have this guy equals 1 times cosine t. This guy equals 1 times sine t. Right? We also use this guy here. Okay, and then now solve for x. X is a cosine t, y is b sine t. Okay, so this is an ellipse, and a is the major axis, b is the minor axis, and then we have the center is the origin in this case. So gamma of t is x is a cosine t, y is b sine t, because we want the whole ellipse, so t goes from 0 to 2 pi. And also the orientation is counterclockwise, so this point corresponds to t equals 0. This point corresponding to t equals pi over 2. Here t equals pi. Here t equals 3 pi over 2. And when t is 2 pi, we get to the original point. So far, so good. Let's continue. Example. Parameterize each of the following curves in R3. Describe the orientation. The loop that lies above the xy plane, where the surface x squared plus y squared plus z squared equals 16 and x squared plus y squared equals 4 intersect. Okay, so how does that look like? Let's draw some picture here. So we have in the space, so x squared plus y squared plus z squared equals 16. This is a sphere. This is a sphere centered at the origin with radius square root of 16, which is 4. So we have, this is 4. So we have a sphere centered at the origin. Okay, and how about x squared plus y squared equals 4? Well, this guy is on the xy plane, right? So on the xy plane, we have x squared plus y squared equals 4. This is the circle centered at the origin with the radius equals square root of 4 is 2. So that's why here we have 2 here, 2 here. So we draw a unit circle. But if we put this guy in the space, okay, what will it do? It becomes a cylinder because the z can be anything, right? So it becomes a cylinder. It will intersect the sphere and it will give us 2 circles. Okay, so let's find that out. So we can make a system of equations. One of them is the sphere. The other one is the cylinder. Okay, when we intersect, we can use substitution. See, I can substitute this to equation 1. Then we get 4 plus z squared equals 16, right? And then we have the z squared equals 16 minus 4, which is 12. So z equals plus or minus square root of 12 is 2 root 3. Okay, so what do we get? Well, we get the chase, okay, is the curve. It consists of points x, y, z, such that x squared plus y squared equals 4, and the z is either positive 2 root 3 or negative 2 root 3. Okay, but see our example, we want to find the loop that lies above. So because it's above, then we don't pick the negative, okay? So because it's at the above the xy plane, so we only pick the positive 2 root 3. Last example, we already talked about how to parameterize x and y. If we have a circle, then x is 2 cosine t, y is 2 sine t. So that's why our parameterization equals 2 cosine t, 2 sine t, and our z is fixed. Okay, then my t goes from 0 to 2 pi, we get the whole circle, the loop. So far, so good? Okay, let's continue. The curve where the surface z equals x squared plus 2y squared and x minus 1 squared plus y squared equals 25 intersect. Okay, let's see what it is. Let me use a different color here. How about pink? Okay, So what's the picture look like? So this is x, y, this is z. So this guy, if it's two-dimensional, we see is a parabola, right? But it's three-dimensional, is a paraboloid. Okay, and z is a function of x and y. Okay, and for a fixed z value, we get this guy equals a constant. Just give us an ellipse. Okay, so that's why. And the let's see. Here we consider it's like x over 1. Here we consider it as y over 1/2. 1 is bigger than 1/2. So that's why here we have the ellipse. The major axis is on the x-axis and the minor axis is on the y-axis. And then is a paraboloid. So we connect them together. Okay. And how about this guy? Well, this guy is a cylinder, right? Let me change a different color. So it's on the xy plane with the center is 1, 0 and the radius is 5, right? So 1, 0 is right here, okay? And then the radius is 5. So we get a circle. So let me draw it better. This is a circle. Okay, so when they intersect, when we put them in the space, we actually get a cylinder. Okay, so when they intersect, we get something like that. Let's figure out what it is. So we formed a system of those two equations. Okay, and how does it work? In this case, we cannot really like use substitution method or whatever, but let's focus on this guy. This is a circle, right? We know how to parameterize this circle. We have x minus 1 is 5 cosine t, y equals 5 sine t, and then we have x is 1 plus 5 cosine t. Okay, now we have x and y, they are a function of t, and then look at z. Z is a function of x and y, so we can then plug in our equation 1 to get z in terms of t. So that is x squared, so 1 plus 5 cosine t squared plus 2y squared, so that is 5 squared 25, and then sine t squared. So this is 1 plus 2 times 5 is 10 cosine t plus 5 squared 25 cosine t squared, and then plus 2 times 25, which is 50 sine squared. And do you know that sine squared plus cosine squared equals 1? So this 50 I can split as 25 sine t squared and another 25 sine t squared, and then I can use the 25 sine t squared to couple with the 25 cosine squared. This will give us the 25, and I still have another copy of 25 sine squared. Now let's combine the constants. 25 plus 1 is 26, and then we have 10 cosine t, and here we have the 25 sine t squared. Okay, so now we have got x is 1 plus 5 cosine t, y is 5 sine t, z, sorry, we don't need to put the y here, just put 5 sine t here is okay. Oops, let me see. And z equals 26 plus 10 cosine t plus 25 sine t squared. Alright, and our t goes from 0 to 2 pi. Then we have the whole circle, and then we get a whole loop. So far, so good, everybody? Okay, let's continue. Determine which of the following functions parameterize the curve y equals x cubed. Okay, so let's look at the first one. So here y equals x cubed, which means we know x is t, y is t cubed, right? So let's plug in y is t cubed there. So t cubed equals x is t cubed. Is this true? Yes. And then second one, okay, x is t cubed, y is t. So y, we plug in y is t, and then x is t cubed, but we also have x cubed. Is this true? No. Okay, let's look at this. Y is t, and then x is square root of, so cube root of t, and then we have x cubed. So is this true? Yes. Okay, next, y is t to the 6, and then x is t squared cube. Is this true? Yes, right? So this is what. So that's why we can have for a function we can have many different parameterization. Next, sketch the curve parameterized by of t equals e to the t and e to the 2t. Okay, what's the relationship between e to the t and e to the 2t? We know e to the 2t equals e to the t square, right? And then we know this is x, this is y. So let's plug in. So we place e to the 2t by y. We place e to the t by x. Then we get y equals x squared. Now let's look at the domain. Okay, so for a curve, you not only the formula, but we also know like what are the pieces, what is the t goes about. Okay, so here, because x equals e to the t, and you know e to the t for exponential function is always positive. Okay, so that's why here my x is always positive. Well then, what is this guy? This is a parabola, right? But my x is always positive. So this is the origin. We don't include the origin, and then we have the parabola. Now let me draw it better. So it passed through 1, 1, and 2, 4, etc. Okay. So this is our answer. And so I strongly recommend you to use the graphing software GeoGebra, because sometimes in the space, if we don't, maybe it's hard to imagine what the curve or the surface looks like. And so then it's very good to use the graphing software to help us to visualize the surface. Okay. So let me show you in the next video how to use GeoGebra to graph the surfaces. Okay, see you soon.